In early 2014, STEM Scouts in the Pathway to Adventure Council in Illinois were told there was an opportunity for their troop and crew to participate in a NASA experiment on board the International Space Station. The real estate for their experiment would have to fit in a box that was 4 inches by 4 inches by 6 inches. Each scout was given a 4x6 card and told to write down their idea for an experiment in one sentence. At the end of the night, they had collected 84 ideas. By the next week, the 84 experiments were reduced down to 4, and the following week, they agreed to combine 2 ideas into a single experiment that would fit the requirements. STEM Troop and Crew 209 had taken the first steps to being launched to the International Space Station. We'll learn more about this incredible opportunity for scouting to partner with NASA and contribute valuable knowledge to the scientific community in this edition of Artifact of the Week. Recently, we were contacted by Norman McFarland, who wanted to know if the museum would be interested in receiving a display of the science experiment designed and built by the Scouts from STEM Troop and Crew 209 and actually launched and conducted on the International Space Station. Well, of course, we said yes, so earlier this month, Norman delivered the displays to the museum. He was also attending a couple of conferences at the Philmont Training Center, so I had the opportunity to interview Norman about the experiment and the materials he was delivering. I asked Norman to explain the experiment they chose to conduct.
And that one that we chose was, does an organism mutate at a different rate in low gravity of space as compared to Earth gravity? We then set about how would we do this. The microbiologist on the team, one of the mentors, explained something called an Ames test that is typically used to see if something is a carcinogen. But if we started off with a carcinogen in the mix, we could see how long it took before it mutated, the items mutated. Conveniently, with an Ames test, the organism's solutions start off purple. When there's mutations, they turn yellow. So we could test for mutations with a camera.
For their test, the team chose to use E. coli as their test subject. They recruited a microbiologist to assist and serve as an adult mentor for this part of the project.
The E. coli that we sent up to space was divided into 8 different concentrations. One was considered a positive test, and one was a negative test. So the positive test had to have a whole bunch of yellows, and the negative test had to have a whole bunch of purples.
The Scouts also knew they needed data that was statistically significant for any valid scientific information to be gained. For this, they called on another adult mentor to help them determine how much data they would need to collect.
So another one of the mentors was a numbers guy and figured out how many samples we would need to be scientifically significant. And it turned out that it was quite a bit more than we could fit on one surface of the what we had space-wise. So some good brainstorming, and there was a lot of brainstorming in this, by the way. Some good brainstorming, and we decided that rather than a flat panel with the wells holding all the, that's the holes where you put the E. coli, rather than making one flat one, we would make a carousel and put in enough to get up to the 560 we needed to be significant, scientifically significant. That was the basis, but then we said, while we're there, we should monitor temperature, humidity, and all kinds of other environmental variables because we're going to run the test twice. Once we're going to run it in space, and then when we get results back from space, we're going to run it a second time on the ground, and then we're going to compare the results, the pictures essentially, and come to our conclusion. So we did run the experiment twice, as I said, and there were separate modules for that. Initially, we were going to run them at the same time, but it was suggested that we get results back from space and then do any tweaking we needed to do to the algorithms to get a better ground test. And that's what we did.
As Norman mentioned, they used cameras to capture images of the E. coli, but this introduced new obstacles to overcome.
We couldn't get a lens that would let us see the entire subplate. So we put in two cameras. So we had an upper and a lower. And we had 8 of the panels. So we got 16 pictures, theoretically every hour. And that got written onto the SD drive on the controller board. So we were expecting some 9,000 pictures back.
They also had to figure out a way to light the bacteria wells and to rotate the wells so the camera could see each panel for the image to be captured. All of these were overcome by a group of scouts aged 12 to 20 years. The boys came up with the idea of using colored fingernail polish to mark the top and bottom of the carousel.
We were concerned that for some reason the carousel wouldn't turn, so we put color marks at the top and bottom of the carousel. We asked one of the boys to ask the neighbor next door's daughter for different colored of nail polish. And yes, they had it, all colors. So that way the camera would always tell us which panel we were looking at.
I asked Norman what he thought was the biggest challenge the scouts had to overcome to complete this project.
We had many discussions on how we start the experiment. So the E. coli was going to go to space dry, and the starting point was going to be when we injected water. Well, how do you inject water to the outside or inside of 500 wells in a carousel? Well, you can't do it inside because the cameras are in there having to look into it. And we spent, like I said, immense amounts of time on this. And we would divide off into groups for brainstorming, and of course, standard rules. No idea is bad. We can look at every idea. So 2 of the boys were over in the corner kind of laughing the whole time one night. And we asked them to do their presentation. And their idea was to use steam to get this thing started. And then as they finished, and I'm thinking to myself, okay, it's not a bad idea, but I don't see how to implement it. One of them said, what if we just freeze it? And they sat down. Well, it occurred to us, if we freeze it, when you get it on station, it's going to thaw, probably about evenly spaced. And so that would work. Then we had to see if the E. coli would survive that. So microbiologists went and did some studies. And eventually that was how we went to space.
Now that we have a good idea of how the experiment would be conducted, I asked Norman about the scouts on the project. He said the project started with about 24 scouts, including 2 girls from the venture crew who dropped out of the project very early on.
So we started off with roughly 20 boys, and we divided them into various groups. We needed someone to understand basics of electronics for a closed loop system, somebody to know mechanicals, some software, some people to understand the cameras and the focal lengths and all that sort of stuff, and just on and on. So we started off with basic training, and then as we got a few months into it, we rearranged everybody so that there was one of the electronics guys, a mechanical guy, and a software guy all on a team to do motor control, or to do the cameras, or to do the sensors, and so on. So each group kind of focused in on their area, made their sub-assemblies, prove to themselves that those sub-assemblies were working. And we put all that together, made it work as a unit, did some redesigning and fixing, and eventually got to the point that the boys said, let's go to space.
Norman told me that as the project went along, they had to make adjustments to who was doing what and how they managed their time and the tasks that needed to be completed.
There were 20 kids at the beginning, and we, as scouting does, allows kids to come in and go out. We started in roughly March, April timeframe of 2014. We launched to space in August of 2017, so roughly 3.5 years. The catch to this was if you're in school and you need to teach a piece of science for your project, you could do that in a science class. You can't do that in a Boy Scout meeting. As we said, each of the teams were 4 boys. Well, on the first night, 1 boy would be missing. The next night he would be back, but the second one would be missing. The next night, and so on. And so you never had everybody in the same room learning the same thing. And so that kind of adjusted how we ran the project. We lost people along the way. So by the time that we were actually building things that were going to go to space, we were down to 10 scouts. We had roughly 2,500 hours logged for scouts working, and we had just about an equal number of adult hours. We never had scouts touch the E. coli or be near the E. coli. That's not in Guide to Safe Scouting. The microbiologist did that in his lab under lab conditions and so forth. When we started, NASA cases wanted people 12 and up, and we had 2 boys that were 11. Just started scouting. I don't think one of them had even earned their tenderfoot yet. And he was a science geek. And he came up and he said, I'm not old enough for that. I want to do this, but I'm not old enough. And I said, I want you to come to all the meetings. I want you to be just another participant because you will be 12 by the time we launch. Oh, okay. So 12 to 18, once they aged out of scouting, they aged out of the project. And we had scouts age out each year going through.
In total, the scouts and their adult mentors logged more than 5,000 hours on the project. Norman told me that as the local media learned of the project, they asked the scouts if they had plans for watching the launch and asked if they could cover the launch. The scouts said, sure, we'll see you in Florida. Norman said the scouts were invited to the Kennedy Space Center to watch the launch and had the opportunity to sit in the same seats as the families of the Apollo astronauts as they were being launched to the moon. Next, I asked Norman to take me through the displays they had created and explain what we were looking at.
This is all the different types of assemblies that the scouts dealt with. So we wanted to measure things like what's the temperature in the box, what's the humidity, how much, that was this sensor. This is a camera module without the lens, and I think that's the camera there. This is called a Nessie board. This is the space in here. You see the SD cards. You see connectors all over the place where various types of interfaces came out. There's a microchip right in the middle that was really flexible and was really the heart of the experiment. This is a radiation sensor. Since we're in space, we wanted to get some idea what radiation was going on with us. This is one of the support plates. You can see the holes where the E. coli was put in, and it's like a 14 by 5 matrix. And we had 8 of those. To get all the wires from here out to all of these, we had to do all kinds of interfaces. Well, the first time we sent that down to NASA, they said, oh, too much wire, too much wire. If something starts to burn, that'll put too many noxious things in the air. So we went back and the boys designed a camera module that was inside and held the two cameras and wired out to the controller board. And then secondly, we had the real-time clock, the stepper driver, a few other things on this board. The boys designed both of those boards. Almost the night before we were going to get ready to go to send stuff to Florida, it occurred to me we could put our names in space. And so I got the time records and I broke everything down to who were the scouts. We called them members, who were the mentors, and then who were people that had started on the project but later had to drop out for whatever reason. So they had contributed, but they weren't there at the end. We put their names in there as well.
Wiring was another engineering consideration the Scouts had to address.
We started off thinking along the lines of we'll just wire up some breadboards and it'll work fine. It'll let us do the crisscrossing from Nessie board connector to the sensors. And because it was like we'd work for an hour, then we'd go home, we'd come back, we'd package this thing up. The connectors were breaking all the time. So we went to a plated through hole board instead of a just open board and made these. And you can see all the wiring connections and back and forth. In the end, this whole interface thing here got replaced by the board with a real-time clock on it on the first panel.
Selecting a motor to rotate the housing became a trouble spot for the Scouts, according to Norman.
We had trouble with motors, so we ordered several different motor types and just sat down one night and played with each of the motors. We had mechanical stuff to do. So I gave you an example of the motors. In the end, the stepper motor was chosen, and it's this one here.
We then turned our attention to the ground unit and the unit that traveled to the ISS.
This is the ground unit, and this one has been expanded out so you can see the many parts, starting with the carousel, the aluminum work, and then the individual plates that held all the E. coli. That was set inside of this. And in this, you can see the camera assembly board and the camera lenses and the lighting panel back here. So we would rotate, the lights would come on, upper camera take a picture, lower camera take a picture, rotate again, do that 8 times. This is the stepper motor assembly, and it's got like some other little stuff on it, but that coupling there would tie to a shaft on the carousel. And then down here, you can see the Nessie board and our interface board with the limited amount of wiring that was required to do that. So that would all go together, this piece into here, this would go over, and then this fastened in here. By the way, all the aluminum work here on this and this was done by a 6th grader in his basement. His dad happened to have a milling machine. It got loaded up and ran for about 80 days, as I recall. It was a really long run. This is the unit that went to space. We left this one intact so you could see how it fit together. Everything had to be inside the 4x6 box. And then you see the last minute ad, which was our team. We used Ames tests for everything. So our project name was Our Team Aims for Space, using the Ames test spelling. And that was the top right there that you see with all of our names on it.
I asked Norman about their interactions with NASA and any astronauts.
So they went down to NASA. A couple of guys went down early, 2 adults, 2 scouts, and did the final assembly. We have a picture of them handing the unit to NASA. I guess it was to cases to put on the rocket, and we were done. We had no astronaut assistance other than they take it out of our box and plug it into their assembly, and at the end they take it out of the assembly and put it back in our box. I think that the astronaut time to us with a bargain rate was about $50,000 an hour.
In all, the experiment ran on the ISS for about 30 days. I asked Norman about the results.
NASA had requested that we use a radiation hardened disk drive, SD card. When we bought those, we went from 64 meg to 32 meg, and we found out afterwards that a 64 meg uses a file structure called FAT32. The other one uses FAT16. The smaller one uses FAT16. That means that in a FAT32, you can put an unlimited number of files in the root directory of the SD card. But in a FAT16, you can only put 128 files. We had 126 pictures, we had a sensor results, and we had a configuration file. And after that, no more data came back. So when we looked at all the stuff, when we came back from space, we kind of freaked out, to be honest about it, and then started digging into it.
After the experiment returned from space, Norman described what happened next.
We had a night. I had gotten everything back from NASA. So we sat down at a table in the basement of the church, and we slowly took things apart. Everybody wanted to just get in there, and it was, no, let's take the stuff out of the way that we don't need and dig, So then once we got inside, we could reach the SD card. We immediately made 3 copies of that, so nothing would get lost. And then we started looking at the SD card and went, oh dear. And so the immediate mood was, we blew it. But scouts bounced back, and let's find out why. So it was almost immediately, what went wrong? But once we started saying this is what happened with the sensor mistake, one of the boys said, oh, I know what that is, and type a poka, and changed a little program here and there, problem solved. Took us a little bit more time to figure out the cameras and the number of files, but we kind of specified this is what we have to do, and they just went and did it. So it was immediately, there was a lot of depression, but within a week we were back to full force. Get the ground unit ready, let's get that thing going. Of the 10 boys that put in the majority of the hours, 8 of them became Eagle, earned their Eagle, 2 aged out, and many of them have said their college major was picked by what they learned on the space station.
Very cool.
So when cases came to us, they wanted us to teach engineering to the boys. And at one point, just before launch, we asked, what is success and what is fail? And, well, we're going to have 9,200 pictures. We're going to have all kinds of sensor. And somebody said, what if we don't get all 9,000? What if we only get 1,000? Well, what if we don't get that many? And they kept working back. And finally, one of the boys said, the mission of this was to teach us engineering. That's been done. It doesn't matter what comes back from space. And I thought that was a very novel That gentleman, by the way, wants to become a manager.
Ultimately, that scout was correct. It wasn't the results of the experiment that really mattered. It was the opportunity, the exposure to something new, and maybe a little out of their comfort zone. It was an opportunity to believe a group of scouts could be a part of something much bigger in a meaningful way.
The length of time and amount of dedication it took to do this project makes it hard to replicate. But I would like to see the STEM program expand to making systems. We do this in the robotics area, where we have hardware, software, mechanical, electrical, all working together. I would like to see them doing more of that with end goals where you start with, here's what you have to do, and end with, see, I'm doing it. I think that would help the scouts a lot and teach them life skills.
Well, that's all the time we have for this week. Join us next time as we continue to learn more about the history of Scouting America through the collection of the National Scouting Museum and Artifact of the Week.